Hello and welcome to video number 2 in the series of examining the most accurate clock on Earth. Today's video is a hiccup in my research into the Foucault Pendulum. I may be able to continue on my research with the clock, but it may bring a halt to my Foucault Pendulum research. The situation has arisen where I've been studying this pendulum for probably 10 years, and I've probably overlooked a very important factor which I will need help for. So if someone can help me with this and my basic understanding of physics, I'd appreciate it. The thing that we got probably wrong for 170 years is the Foucault pendulum in the Pantheon in Paris demonstrating the Earth is actually stationary. So we watch this pendulum, everyone's been watching this for 170 years, and we've all overlooked a basic vector. Probably the best way to put it. Now, before I start a war with France and Australia, I know this is their sacred cow, so I know for a fact I'm wrong, but I can't get over this yet. So, it's been examined by the greatest minds in physics. It's been taught in physics for 170 years. The greatest colleges and knowledge and universities have been teaching this Foucault pendulum. Most likely I'm wrong. Okay, so here it is. This is where I've come up with. Should the Foucault pendulum swing in a straight line, in an ellipse, or in a figure 8? Now this question has been bugging the Foucault pendulum makers for forever, since the thing was invented. And we all come to the conclusion, myself in fact, that the pendulum should swing in a straight line without any elliptical or figure 8 movement. And certainly the Foucault pendulum in the Pantheon definitely swings in a straight line, and has been swinging in a straight line for 170 years. So why even think about this ellipse or figure 8? Now, from my research, my early experiments would travel in figure 8s and ellipses because there was imbalances and inconsistencies in the pendulum, mechanics and the energy train all the way to the bulb. And it's documented everywhere. If you've seen an ellipse or you've seen a figure 8, you've got something wrong with your mechanics or your balancing of your pendulum. So, sort that out. It should swing in a straight line, just like the one in Paris. Right, clear. Okay, let's stop now and we'll break this down into baby step experiments and see where I've gone wrong. So just let's go now to an experiment setup. Thanks. Alright, let's go with the easiest analog to understand. Here we have our Earth turning clockwise at the North Pole. Here's our North Pole. So if we place our pendulum on the North Pole, and our swinging pendulum will stop in a position because of the momentum, the combination of momentum and mass. We can create a virtual frame of reference in space. Shown by that yellow sticker. No problem. Everyone can relate to that, and it will be a straight line. The pendulum will swing in a straight line. The same condition will happen if we turn the Earth off and it stops revolving. We have a stationary Earth. The same condition will arise. So in theory we haven't picked the difference between the stationary and the revolving Earth. If our pendulum is actually working according to Foucault's formula, where we have enough mass and enough inertia, enough momentum to overcome the friction and decouple from the Earth. So, no problem. Our problem arises when we go to a different part of the Earth, because no one is actually on the North Pole or the South Pole of the Earth. So we have another condition, which is this condition. So our problem occurs when we relocate our pendulum, not from the North Pole or the South Pole, but somewhere else on the Earth, rather than the equator, which is 99.9% of the population of the world lives. So let's get our pendulum going. And if the Earth is stationary, once again we get a straight line and locate it to our fixed point in space. However, now when we turn the pendulum on, we still have our point fixed to space, which is a combination of the momentum, mass and velocity, no problem. However, we have now a vector that we didn't consider. A vector of a rotary vector going around the Earth. So the pendulum, although it's fixed to the point in space, doing its thing, which it should do, it's got this other vector as it goes around the Earth. Alright, let's return to the blackboard and get some more detail on that. Alright, so here we are trying to analyse this unusual predicament. It happened when I started phasing my pendulum using these universal joints. I started to get elliptical and figure 8 configurations happening, depending on how I phase this universal joint, these two universal joints, which actually made sense because I was actually isolating each vector. We have our vector that we know of, which is the one that we just set with the straight swinging motion. Then there's this vector we know that could be there because of the friction of the Earth grabbing the pendulum and swinging around. But the biggest, which almost a very strong vector came in, which was this rotary angular velocity, angular momentum vector. So virtually what we got is a crank handle, which is, as this thing goes around, we have a centre point, we have a pendulum swinging down here on a crank as it goes around. So I don't know, it creates this elliptical, certainly creates an elliptical, in fact it almost mimics this shape here. The elliptical orbit is like this. As the pendulum swings, it starts off dead straight, which I have a demonstration. Let's make this video will be too long otherwise. So then it starts off swinging in this direction, back and forth, and the ellipse seems to work out bigger and bigger as it goes around. So there's the centre point. As it swings, it creates this ellipse. Now it goes clockwise or anti-clockwise, and that can be sort of a bias thing. Alright, so probably to sum up, something to think about. I don't expect an exact anyone to come up with a solution straight away. Remember, this thing has been going for 170 years. So chances are I've made some silly mistake and haven't overlooked something. So anyway, just think another little thing had happened while I was actually playing with that little pendulum on the rotary table. I noticed that if in the centre of the Earth, at the North Pole, a strange thing happens. We virtually can lift that pendulum straight off. If it decouples from the Earth, that's more or less like as if a helicopter just lifted it off and it just sat there. Now, all of a sudden it's isolated from Earth. Strange thing came through my mind, it's no longer influenced by Earth anymore. So will that affect time? So just perhaps another thing for our clock to think about. Does time change as we leave the Earth? All right, something to think about. All right, thanks. Hopefully that follow-up video showing you the elliptical orbits coming from this phasing these universal joints is a pretty quick way. So I'm thinking that's only a few days away. Thanks for watching. See you in the next video.